Hello students, welcome to the next lecture on the complex analysis. Today I will explain you the concept of the Mobius transformation. That is one of the most important topics in the complex analysis. Myself Dr. Harish Garg, you can follow and subscribe my YouTube channel. Now what is the content behind this today's lecture? We will understand the concept of the Mobius transformations. Later we will explain the concept of the Riemann spheres and the extended complex numbers. And finally I will explain you the certain examples to understand the concept of the Mobius transformations. Now what we have discussed so far, we have understand the concept of the linear transformations which are defined as W is equal to AZ plus B, where W is defined as U plus iota V, Z is defined as X plus iota Y, such that the transformation W is equal to T of Z. Based on these properties of the linear transformations, we have studied the concept of the rotations, magnifications, translations, and one more property that we have discussed in our last lecture is inversions. The details of these lectures you can find at my YouTube channel, and you can find the playlist of the complex analysis. You can see the concept of the inversion, magnification, rotation, translation, complex linear transformation, conformal mapping, and many more lectures available in this playlist. You can subscribe my YouTube channel so that when I upload the next video, you will get the notifications. Now if you closely look about the given function that we have discussed so far, this is defined as a linear AZ plus B. So if you consider the complex function, that's a ratio of the two linear function AZ plus B, CZ plus D, where A, B, C and D are my complex constants. Fine. Complex constant means because the variable is my Z, that means A, B, C, D are independent of Z. Fine. Such that the relation between the A, B, C, D is AD minus BC is my non-zero. That is A into D minus B into C is my non-zero. Or in other words, if you write in terms of the matrix A, B, C and D, so clearly say AD minus BC is basically my determinant of the transformation. Fine. So it's a non-zero. Non-zero means it can be positive, it can be negative. Then this transformation T of Z is AZ plus B is called as linear, because they are the linear fractional transformation. Also this ratio or this transformation is known as the bilinear transformation or Mobius transformation. As I mentioned you, AD minus BC is my non-zero. Fine. So that means it may be positive or it may be negative, and the quantity AD minus BC is called as the determinant of the transformations. And whenever the value AD minus BC is equal to 1, then we call as the normalized bilinear transformation. Another important concept is, as we know, the value of the W is defined as T of Z, and the value of the TZ in the Mobius transformation is AZ plus B over CZ plus D. So if you cross multiply them, you will get CWZ plus W of D minus AZ minus B, which is equal to 0. Fine. Now if you closely look about this equation number 1, clearly say the equation number 1 is linear in which variable? Linear in W as well as linear in the Z. But make sure the equation number 1 is non-linear. Fine. Degree is 2. But if you closely look out only as a variable W, then you can see that degree is 1, degree is 1. When you look about that only W, then the Z is my constant. If you closely look about only on the Z, then W is my constant. Now because equation number 1 is linear in how many variables? Linear in the two variables. Fine. That's why this equation number 1 is called as bilinear transformations. Another case, because AD minus BC is equal to non-zero, but what will happen if your AD minus BC is equal to 0? What will happen if AD minus BC is equal to 0? So I can take an A is common from the numerator, then it is B over A. I can take an C common from the denominator plus D over C. Now AD minus BC is equal to 0. That means AD is equal to BC. Fine. If AD is equal to BC, what does the meaning of the B over A? B over A is nothing but D over C. Now clearly say B over A is equal to D over C. That means these values are cancelled. The expression becomes A over C. And A and C are my constants. Therefore, the transformation is always constant whenever AD minus BC is 0. Therefore, you can say AD minus BC is non-zero is one of the necessary condition to define the Mobius transformation. Another concept. Now, because AD minus BC is my non-zero, fine. So we will consider two cases provided whether the C is my 0 or non-zero. What will happen if C is my 0? If C is my 0, then your expression becomes A over Z plus A over D into Z plus B over D. Now clearly say because A, B, C and D are my constants, so this equation is called as linear equations, fine, or linear transformations. Furthermore, because C is equal to 0, then the expression of AD minus BC, fine, if it is 0 or if it is non-zero, because this number is my 0, that means AD is my non-zero, fine. Second case, if C is equal to 0, then you can write the quantity again. I can take an A is common, then it is Z plus B over A. Similarly, from the denominator, I can write is a Z plus D over C. Fine. So now because the degree of the numerator and denominator same, I can add D over C. I can subtract D over C. Fine. So how you can write that? You can see A over C is outside. Now you can separate them. It becomes 1. If you take the LCM, it becomes BC minus AD divided by AC over Z plus D over C. Is it okay? Now you can open this bracket. What will happen? The first value will be A over C. Second bracket, A and A will be cancelled. It's a C square. BC minus AD over C square into Z plus D over C. Or if you take the LCM, it is a CZ plus D. Fine. Now the first result is what is the domain of the Mobius transformations. So clearly say domain is all those complex numbers apart where the denominator is my 0. This is my domain. Fine. Domain is all those complex numbers such that Z is my not equal to minus D over C. Now, as we have discussed, we have studied the concept of the, what we have studied is in this previous lectures, we have discussed the inversion, magnifications, rotation, translations, and all are considered as the special cases of my Mobius transformations. How? You can see in case of the translations, if I substitute A is my 1, C is equal to 0, D is equal to 1, then you can see the Mobius transformation becomes translation. Similarly, in case of the rotations, if I choose A is equal to e raised to power iota theta and clearly say this is a constant number independent of the Z, B is equal to 0, C is equal to 0, D is equal to 1, then again you can see that translations, Mobius transformation becomes my rotations. In case of the dilations, if I substitute A is equal to K, B and C both are 0 and D is equal to 1, then the Mobius transformation becomes dilation. Dilation is also known as magnifications. And the last case is if you take A is equal to 0, B is equal to 1, C is equal to 1, D is equal to 0, then the Mobius transformation becomes inversion. Moreover, we have discussed in our inversion lecture, what we have discussed in the inversion lecture is W is equal to 1 over Z is also known as reciprocal functions. Moreover, the W is equal to 1 over Z is my non-linear functions. And similarly, T of Z, that is the Mobius transformation, is my non-linear function. Now, once we know the Mobius transformations, The special cases of the Mobius transformations are translation, rotation, dilations, inversion. The first result hold is every Mobius transformation is written as the composition of these functions. What is the meaning of that? If you have the Mobius transformations, then again we will consider two cases. The case 1 is when c is equal to 0, case 2 is when c is not 0. If c is equal to 0, then what is my transformation? A over d into z plus b over d. And whenever c is my non-zero, then we have defined this category. And you can see that bc minus ad is just like say determinant. What is the meaning of the composition? That means, can you write this function is t1 composition t2? Fine. Or I can written this is s1 composition s2 composition s3 and so on. Fine. But make sure whenever we are talking about the compositions in the Mobius, it is always in the even number. What is the meaning of the even numbers? You can see I have used a 2, so n is equal to 2 is my even. But if I chosen as only 3, then n is equal to 3, which is my odd. That means this is not possible. So I have to either write as a s4 at least. In that case, n is my 4, which is my even number. Fine. So it's a very simple. How you can prove that is a composition? So look at the first case. If I write only for the first case is, how you can write that? If I write this that t1 composition t2, can you find the value of that t2 of z? Can you find the value of that t1 of z? It's so very simple. You can see these are my constants. Fine. I consider b over d is my another constant alpha, and a over d is my another constant called as the beta. So the equation becomes beta z plus alpha. So I can define the one mapping is beta into z. So I can say beta is my a over d into z. Fine. And another one is z plus alpha. Alpha means b over d. I can define the two mappings. Fine. Where t1 is z plus constant and t2 is my variables. So then clearly say t1 circle t2, that is a composition. So it will be t1 of az over d, and if you substitute the value, it becomes az over d plus, and which is same as t of z. Now case number 2, if you have defined this category, then you can define the s1 of z. So I can start from the previous one. This is the one z. I can define as a z plus d over c. I can define the s2 of z, which is a 1 over reciprocal. I can define 1 over z. Third case s3, because this all numbers are my constants. So clearly say because a, b, c, d are my constants. So I can write this number is bc minus ad over c square into z. And the last case is again a over c is my constant plus this quantity z. And based on these four functions, you can define that t of z is, firstly you can define as s4 a over composition s3 composition s2 composition s of 1. Fine. So s1 s2 s3 s4, and based on that you can define the composition is s4 circle s3 circle s2 circle s1, and you can see how many composition you have taken, 4, which is always even. Now the second concept is, what is the meaning of the extended complex plane? What is the, or you can also call as the Riemann sphere or call as the closed complex plane. Remember, our target in the case of the Riemann sphere or the closed complex plane is how we can introduce the point infinity into the complex plane. Fine. So our target is to include the idea of infinity into the domain. Now, what is the meaning of the extended complex planes? Your target is to find the value of the z so that t of z becomes infinity. For example, if I define the function t of z is z plus 2 over z minus 1. So clearly say whenever z approaches 1, t of z becomes infinity. So whether the z is a part of the domain or not. Fine. So the function t of z, or f of z becomes infinity as the variable z is equal to z naught. So our target is to discuss that kind of the situations. So now in order to understand the concept of the infinity, we have to introduce the concept of the extended complex plane. The extended complex plane is also known as the Riemann sphere, and it is denoted by C of infinity, or sometime it is denoted by C cap, sometime it is denoted as a C bar or C cap. What is the meaning of the C infinity is all those complex plane union infinity. Fine, but make sure what is the meaning of the C is this is the x plus iota y, and in this case infinity is my point, not as a number. It's the infinity is my point. So we can extend it the original complex plane by adding a single point. Remember, in the real R you have minus infinity to plus infinity, while in the complex plane infinity is considered as the point in the Riemann sphere. So we can define the C of infinity is C union. So C union infinity is a point. Remember that. Now, what is the meaning of the infinity? So whenever we are considered the Riemann sphere or extended complex plane, the point infinity is near to the very large number. Fine, as similar to the point 0 is near to the very small number. Now, how you can based on this complex plane, how you can define the complex number? So again, once we have defined the complex number is x plus iota y, where x and y belongs to the R. So what is the complex number is? Again, we can define is collection of all those x plus iota y's union, because infinity is my point. Infinity is my point. So we can define the complex number C together with the infinity. Make sure students, you can never write infinity in this manner, infinity plus iota infinity. This is not true. Again, you can never say infinity plus iota into y, because in the real line we know x plus infinity is infinity. Fine, infinity plus x is equal to infinity, infinity multiply x is equal to infinity, but because in this case in the complex plane infinity is my single point, so you can never write in this manner. Fine, so it is not be true like if I say 1, so 1 I can written as 1 plus iota 0, but infinity you can never write in this manner. So this is only the point which we are defining for the infinite cases. Again, because the complex numbers are does not form a field, unlike the complex number, the extended complex plane, that is a C union C infinity, does not form a field, because we didn't find the any additive or multiplicative inverse corresponding to the infinity. So what is the importance of this extended complex plane? That means whenever we can define the mapping, say 2 plus z over z minus 1. So clearly say this function is my not analytic. Fine, because the function value at the 1 goes to the infinity. But once it is not analytic on this C. But if we extend the domain, from C to C infinity, what is the C infinity is C union C infinity, then clearly say the mapping T is my analytic. Okay, fine. So what does it mean is, so whenever you are whenever you are using the extended complex number, any mapping, any rational function mapping can be extended to the holomorphic functions. Why? Because wherever the domain goes to the infinity, the function values goes to the infinity, that point you can map to the infinity point. So therefore, that's why this extended complex plane play a very important role. So you can extend it any functions to the holomorphic function. For example here, so clearly say what is the value of that T of plus minus 1? It goes to the 0, while T of 0 is minus 4. Similarly, T of 3 you can find at 9 plus 4 is 13, 9 minus 1 is 8, and so on. Fine. So that means plus minus 1 is infinity. That means this function is not analytic on the C, but this function is analytic on C infinity. Fine. So using this definition, we can say that T is a continuous mapping from the Riemann sphere, that is a C infinity to C infinity. Fine. T is a mapping from C infinity to C infinity. While T is not continuous map from the C to C, but it is a continuous map from the Riemann sphere or extended complex plane to extended complex plane. So, or we can say any meromorphic function we can thought as the codomain is my Riemann sphere, then we can extend it to the holomorphic function. Now, can you find the image? Image means if W is equal to T of Z, so W is my image. So your target is to find the value of T of 0. Your target is to find the value of T of 1 plus iota. Your target is to find the value of T of iota and T of infinity. Fine. So what is the T of 0? First of all, you can see whether it's a Mobius transformation. How you can check is a Mobius transformation? Only thing you have to check is AD minus BC is not 0. In this particular example, A is my 2, B is equal to 1, C is equal to 1 and D is equal to minus iota. So what is the AD minus BC? Minus 2 iota minus 1, which is non-zero. Yes, it is a Mobius transformation. What is the value of the T of 0? 0 plus 1, 0 minus 1. It is minus 1 over iota. You can rationalize them. It's a minus iota over iota square, that is iota. Similarly, you can find for the second number T of 1 plus iota. So you can substitute 2 plus 2 iota plus 1 and it's 1 plus iota minus iota. So that will be 3 plus 2 iota. Similarly, for the third case, it's a 2 iota plus 1 and iota minus iota, that is my infinity. So because my domain is C infinity to C infinity, yes, it is well defined. And what is the value of the T of infinity? We can take the limit as Z approaches infinity of 2Z plus 1 over Z minus iota. So if you divide by Z, it becomes 2 plus 1 over Z, 1 minus iota over Z. As Z approaches infinity, answer becomes 2 is the right answer. Look at another one. Consider the linear transform. Consider transformation. Your target is to find the T1 inverse. Fine. Now look at that. T1 is a Mobius transformation or not? First of all, our target is to think whether T inverse exists or not. T inverse exists only if you prove that T1 is my Mobius transformation. Fine. So how you can prove the Mobius transformations? So look at that. What is the A? A is my 1, B is equal to 2, C is equal to 1, D is equal to 3. Then what is the value of the AD minus BC? It's a 3 minus 2, which is non-zero. Yes, T1 is my Mobius transformation. Once the T1 is my Mobius transformation, therefore T1 inverse exists. And how you can find that T1 inverse? So you can see W is equal to T of Z. Now W is, so what is the value of that T1 inverse? So T1 inverse of W is equal to Z. So my target is to find the value of the Z from T1. Fine. So that's, I think, is so very simple. We can state it as Z plus 2 over Z plus 3. I can cross multiply them. Wz plus 3W minus Z minus 2 is equal to 0. My target is to find the value of Z. So it will be 2 minus 3W and the Z value will be 2 minus 3W divided by W minus 2 is the required T1 inverse of the function. Similarly, you can find the T2 inverse. Firstly, check whether it's a Mobius transformation or not. A is equal to 1, B is equal to 0, C is equal to 1, D is equal to 1. So AD minus BC, which is equal to 1, which is my non-zero. So therefore, we can start with the W is equal to T2 of Z. I can substitute the value. W is equal to Z over Z plus 1 I can cross multiply them. Minus of z is equal to 0. I can take z is common, w minus 1, which is minus w. So, or I can write w is my w over minus w plus 1 is the T2 inverse. Moreover, you can also see that T1 and T2 inverse are also my Mobius transformations. How you can check whether they are Mobius transformation? I can find the value of the A, B, C and D again. In that case, I can compare with AW plus B, CW plus D. A will be my minus 1, B is 0, C is 1, D is my minus 1. Again, you can see AD minus BC is my non-zero. Look at the last case, that's a composition. So we can start from this. What is the value of that T1 of Z? Z plus 2 over Z plus 3. Fine. Now I can substitute the value into the T2. So Z plus 2 divided by Z plus 3. Z plus 2 over Z plus 3 plus 1. If you take the LCM, Z plus 3 will be cancelled out. Then it is a z plus 2 plus z plus 3. So that becomes z plus 2 over 2z plus 5. Again, you can see the transformation is my Mobius transformation. Why? Because A is my 1, B is equal to 2, C is equal to 2, D is 5. Again, you can see AD minus BC is my non-zero. But you can see in journal that is a composition T2 circle T1 is not equal to T1 circle T2 in journal. That's a very important point. For example, if I take the T1 is a Mobius transformation, T2 is again my Mobius transformation, then what is the value of that T1 composition T2? So that number will be 1 over z plus 1. On the other hand, it number will be 1 over z plus 1 and clearly say both the numbers are not equal. Fine. Now, can you solve these 4 examples? You can find the image at the point 0, 1, iota and infinity and let me know your answers in the comment box so that I can understand you can deal with this lecture with full concentration. I hope you can subscribe my YouTube channel. In the next lecture, we will see what is the pole and the critical point of the Mobius transformations. I hope you can share this video with your friends. You can comment on this video as much you like. Happy learning, students. Best wishes, everyone.